order 3?
I think you have the cyclic group and the Z3.
I think, I mean, but Z3 is the cyclic group of order 3.
For
Okay.
order 4, you have
So, right. So yeah, we have to get to order 4 before we finally get something. We get 2 non-isomorphic classes, right? We get the Klein 4 group, or what?
Z2 cross Z2.
That is the Klein 4 group.
Z4, right?
Yeah, Z4 is the other one. So you either get the cyclic group of order 4, or you get Z2 cross Z2, also known as the Klein 4 group.
Okay.
So, and then order 5, well, it's cyclic. Order 6, it's either cyclic or it's Z2 cross Z3, or what else? Well, order 6, it starts to get interesting, right? Because that's the group of permutations, right? Your first non-abelian example right there. You see, then it starts to get interesting.
Order 6, the other one like Z2, Z2, Z2.
Z2, Z2, Z2 is order 8.
Oh, that's right. I forgot that it's 2 to the n.
Yep. So anyway, my point is, even with, and now of course it's a little bit sketch for me to be like you know, equating dimension with cardinality, because dimension is very different actually, but you know, it's analogous and it's pretty, you know, it's pretty neat. So there's like up to isomorphism, a unique one-dimensional Lie algebra. It's the abelian Lie algebra. There are 2 two-dimensional Lie algebras. Either you've got up to isomorphism, okay? So up to isomorphism, so dimension 0, well, I won't write this down, but in 2 dimensions, you can have x, y, and it's equal to what? If x and y is the basis for your Lie algebra, what would the, now he explains that, sorry, I was not going to write things, but just, he explains that, you know, you can basically just say x, y equals to x, and that is the, you know, up to isomorphism. You know, only non-abelian Lie algebra of dimension 2. And he explains that if you tried to play a game and made it a scalar multiple of that you can do a change of basis and get an isomorphism. All right, so he proves in that page 23 of Erdmann and Wilden, that's it. All right, that's the unique non-abelian Lie algebra of order 2. And then dimension 3, there are 3 cases. You have dimension of L prime equal to 0. You have the dimension of L prime equals to 1. You have the dimension of L prime equals to 2. And you have the dimension of the derived algebra equal to 3. All right? Those are your 4 cases. The first case we have a name for. What does it mean for the derived algebra to be 0? Yep, you're talking about the abelian, 3-dimensional Lie algebra, right? That's abelian. And actually the 1-dimensional splits into 2 different cases, as he describes. It splits into 2 different cases depending on, so that this story here bifurcates a bit. So this splits into L prime, a subset of the center of L, versus L prime, not a subset of the center of L. If L prime is a subset of the center of L, then what you get is the Heisenberg Lie algebra, and so you can define, basically it's up to notation. You can say L is like the span of F, G, and Z, where the bracket of F and G is given by Z. And he indicates that a model for this Heisenberg Lie algebra is upper triangular matrices of strictly upper triangular matrices. You could use E1, he says E12, E23, E13. E12, E13, E23, is that right? Is that what you just said?
Yeah.
So let's try it out. What's the bracket of E12 and E13 equal to? Is that right? Now you guys you're going to have to remember from last week. I've forgotten my rules. Rats.
I wasn't here last week, so.
But you studied it earlier today. You have no excuse, sir.
I was watching the video earlier today.
You remember I derived this result? Sorry, I'll have to. Oh man, I didn't want to work all through. You look it up for me, Jacob, because I don't want to reinvent the wheel here.
It's
Just read it with indices. IJ.
bracket EIJ equals delta JK EIL minus delta LI.
Minus chronic delta what? E what?
LI.
E what?
KJ.
KJ, okay. Perfect. So when you look at this, we have what? We've got matching I and K, right? 1 and 1.
Oh yeah.
Huh. Well, that's 0. This is 0. That's not it, right? It's not the first two, it's the third. Let's see here, how can I? JK. I want that to be, I'm going to be matching last and first. Matching last and first. Matching last and first. I guess I got to do E12, E12, E23, right? How's that go? See, now I've got J equals to K, right? So this is equal to E13. So this is a possible model of the Heisenberg, the three-dimensional Heisenberg Lie algebra. Because the span, so you can think of this as the F, think of this as the G, think of this as the Z. What's the center? What's the center of this Lie algebra? Let's see here. So if we take E13 with E12, what do we get? If we take E13 with E23, what do we get? Yep, these are both 0. So therefore, the center of L is the span of E13, I believe. See, E13 commutes with everything. It's in the center of the algebra. And as you can see in this case, in fact, the center of the algebra contains the derived subalgebra. In fact, it's equal to it, I believe. So I mean, the L is the span in this case, right? Of these three things I'm talking about. So these calculations show you that E13 commutes with everything. Of course, it commutes with itself as well, all right? So therefore, E13 is a basis for the center. The center is a subalgebra, that you can prove. In fact, it's an ideal, right? Anyway, and when you take brackets, in fact, when you take all possible brackets of these three, the only non-trivial bracket is E13. I'm not sure I've completely proved that, but it's true. So for this particular case, I think it's actually true. I conjecture it's actually true that the derived subalgebra is in fact equal to the center for this Heisenberg. So this is the Heisenberg Lie algebra. And on the other hand, if the derived subalgebra is not a subset of the center, he explains in the book that what happens is you get L prime is, well, L is equal to basically F, well, let me say it this way, GL1 F direct sum with, golly, whatever the name of this thing is up here, Bob. Let's say that defines the two-dimensional Bob-Lie subalgebra. So it's the direct sum of these two things. In this one, there's infinitely many. Such examples. And that's explained in page 22 to 23. And let's see here. And then finally, the last case is this, when the derived subalgebra is three-dimensional. And he says an example of that is SL3. So I think that's actually that's where I want to focus my, I'm not going to worry so much about this infinitely many such examples part. I'll let you guys look at that, but if you want to. I'm going to focus my attention here for the moment on why is it that this is up to isomorphism SL to to F. And here I'm really just thinking about F equals to the reals or the complexes. Okay, so if there's some kind of finite characteristic issue, I'm not going to pick up on it in this lecture. Okay. So all right, what is SL2F? The traceless 2x2 matrices, right? So typical one of those looks like what? It looks like A, B, C minus A. All right. So this is an element of the span of what? Well, the span of, 1, 0, 0 minus 1, 0, 1, 0, 0, or 0, 0, 1, 0. So, all right, so we can write this as E11 minus E22, right? This is E12, this is E21. Behold, if we do E11 minus E22 with E12, how's that go? Let's see here. So these match. So that's E12. And the last and the first match. So that's minus minus E21, I think. If I didn't do that wrong, which is, well, I don't know. I might have done it wrong. JK. 1, 2. IL. And then let's see here. The other one is the outside one's matched, so then K. Oh, got to be careful. It doesn't go 2, 1. What does it do? See the flippity floppeting here? See how this is KJ here, whereas it's JK here? So the fact that I have that pattern, I have 2, 1 here, I have 1, 2 over here. So it's not 2, 1 I put here, but it's 1, 2, and that's good because otherwise it wouldn't be a Lie algebra. Woohoo, that would be bad. So that's 2 E1, 2. Which is fine because that's an element of SL2, right? That's traceless. Yeah. And on the other hand, if I do, let us say, E1, 2 with E2, 1, what does that give me? Well, that gives me E1, 1 minus E2, 2. All right? Anytime you take the bracket of two things, all right, and you get something non-trivial, you've just found something that's in the derived subalgebra. Because the derived subalgebra is the span of all possible brackets. So both of these are in the derived subalgebra. The claim is that the derived subalgebra is three-dimensional, right? I'm 66.66666% of the way there. I got one more. I need to find one more, right? Any ideas? What if I do like E11 minus E22 with, what's the other one? E21? How's that going to go? So I've got E11, E21 minus E22, E21. You start to understand the importance of learning that technical lemma and applying it, as opposed to, I mean, you could work these things out with matrix multiplication, but I do not advise it, right? Because that formula still works for n by n matrices, not just 2 by 2s. So let's see here. Doesn't match nothing, does match, that gives me 2, 1. And this one here doesn't match, does match, so it's the JK, so plus E, oh wait a minute, minus E21? Oh man, say it ain't so. Talk me out of what I just did. JK. Wait a minute, shouldn't that be, that's E11, isn't it? Oh. So it's minus E21. Oh man, I don't want that to be minus E21. That gives me 0. Oh. Really? I really wanted that to work out to what else could I try? Have I got everything? Oh. What about, well, no, the one thing with itself is just 0. That's not it. Oh, man. Well, now I'm annoyed. feel like I've done something bad. Exercise 1.12, 1.12. Find the structure constants of SL2F with respect to the basis EFH. All right, so notation that I should be using. Sorry, I haven't already been using this notation. This is standard notation, by the way. So this guy is E. This is F. This is H. All right. And if we trust exercise 1.12, which I think the answer is in the back of the book because it's got a, you know, one of those little marquees by it. Please be in the back. I was tired. I want to have he claims, this should help me find the error, okay? H with E is 2E. All right. H with F is minus 2F. And E with F is H. All right. So I think this is what? H with E, and we got 2E, so we got that one, right? This one is E with F, right? And we did indeed get it's equal to H, very good. This one here is H with F, right?
So we're off by a sign somewhere.
So what have I done? So it's something exceedingly silly.
Wait, the first bracket, you have L and I are equal. Are you just missing a negative sign up in front of the first 2-1 thing?
Oh.
Yeah.
You say it's here?
Yeah, because we have E11, E21, L and I are equal. So we get negative property.
Oh, it's this term.
Yeah.
Oh.
And you just go to the negative side. Okay.
Duh. Oh.
Yeah,
Yeah, I think you're right. I think you're exactly right. I think that's it. It's just, it has to be that. I mean, that's
Yeah, it has to.
right.
It has to be negative as well.
Okay, so there it is. Proof positive that SL2F is a three-dimensional Lie algebra for which the derived algebra is the whole algebra. Okay? Now, this does not prove, of course, that I have not proved, right, that any three-dimensional Lie algebra with a three-dimensional derived algebra is isomorphic to SL2F. But the argument is given in the book to prove it. So, and it involves some rather, careful linear algebra involving the Jordan form and some other things. So it's an interesting argument. I just I'm going to be lazy and go on. So if you guys don't mind. Is that okay, Audric?
Yeah, I have to like take a picture, write everything you worked down, and zoom it in really to see like what indices are.
Oh, yeah,
Just waiting for you to finish, because I didn't want to.
you're fine. I understand. Okay, so we're going to now ever onward here. So on to chapter 4. And chapter 4 is on solvable Lie algebras and a rough classification is the title for chapter 4. And so here's, he says, to start, we take an ideal of a Lie algebra and we ask when the factor algebra L mod I is abelian. The following lemma provides the answer. Suppose I is an ideal of L, then L mod I is abelian if and only if I contains the derived algebra L prime. All right, so let me write that down. SL2C or SL2F is like very, very important example, all right? So, we're gonna, and the Heisenberg is I think an important example as well. Let's see here. All right, so here we go. Lemma 4.1. I, an ideal of L, then L mod I is abelian if and only if I contains L prime, the derived subalgebra, right, which I have defined carefully right there. So he gives an if and only if proof. Let's see if we can do the same. All right. So let's try it out here. L mod I abelian, right? If and only if what? If and only if what? If we have the bracket of x plus I, comma y plus I is equal to what? Okay, fair enough. That's true. That's the definition. And then that equals to what, though? Right? Yeah. L mod I is abelian if and only if the bracket of any two things in the quotient, the algebra, vanish. What does it mean to vanish? It means that it takes you back to the ideal, right? That's 0.
Oh, yeah.
This is to say it's abelian.
Oh, I see. Okay.
Right? But this is equivalent, right? To saying what? To saying that the LL, well, what does it say? This says that x comma y is an element of I, right? For all x and y elements of L, right? Which is equivalent to saying what? That L prime is a subset of I. Which is to say that I contains L prime.
How long was I out there?
Oh, I don't know. How do you?
My computer reset because it said no more Zoom.
Your computer said no more Zoom.
Yeah.
I saw you blink in and out of existence momentarily there, but I thought it was like somebody interfering with your Wi-Fi or something.
I am on the I'm on the school Wi-Fi right now, so a lot of people. Okay. Okay. We're just in the first. Okay, I can catch it.
So yeah, so I just all I've done is written the proof of lemma 4.1. I'm now on page 28 in the paragraph right after it. So he says, this lemma tells us that the derived algebra L prime is the smallest ideal of L with an abelian quotient. Let me write that out. The derived algebra L prime derived algebra L prime is smallest ideal of L with abelian quotient. Oh, I mean, obviously that's immediate from lemma 4.1, right? So like L mod I is abelian if and only if it contains I contains L prime, right? So the smallest thing that contains L prime is L prime, right? Like you can't get an ideal smaller than L prime and contain L prime, right? So this sentence makes sense. By the same argument, the derived algebra L prime itself has a smallest ideal whose quotient is abelian, namely the derived algebra of L prime, which is denoted by L2, and so on. We define the derived series of L to be the series with the terms as follows. So, definition, L, make sure I get this notation right, parentheses 1 is equal to L prime. L parentheses 2 is it is the derived algebra of L prime, right? Generically speaking, if we talk about the kth derived algebra, it's the bracket of k minus 1 with k minus 1. And that's for k greater than or equal to 2. The way this works is there's a nesting, all right? So here, I'll write it over here. We have L contains L1, which contains L2, and so forth and so on. He says, as the product of ideals is an ideal, the kth derived series, the kth derived algebra here is an ideal of L and not just an ideal of Lk minus 1. So these are these are all ideals of L itself, all right?
When they say product, are they talking about like the brackets when they talk about
That means they're saying that L prime is the product of L with itself. So the derived algebra of L is the product of L with L.
Oh, yeah.
Of course, there's a little fine print there, that span, in man, I'm trying to remember. When we have group theory and we talk about the product of two groups, well, there's no span, right? I think we just take the product of all. You just multiply the elements in one group times the other. There's no kind of like,
Yeah, right. Yes.
yeah. Now furthermore, so this is the derived series. This what I've just written out here on the board is called the derived series. All right. And this is kind of a big deal. Like this is one of those things that if you're taking a qualifier in like, Lie Algebras and you forget the definition of the derived series on your qualifier, it feels really, really bad. I think I may have done that. I can't really remember. I forgot either the definition of solvable or simple, one or the other. I can't remember, but it was, I knew, but for some in the panic of taking the silly test, I forgot the definition of one, and I proved this really, really fundamental, like basic question using like one of like the major theorems of the course. And I think the professor thought I was trying to show off. If he'd understood that I was actually just masking over my ignorance of the basic definition, he probably would have felt differently about my qualifier. So hopefully Dr. Misra is not watching this. Anyway, it's safe. I already have my PhD. Anyway, I think I'll be okay. But where was I? Oh, definition.
You know it now, so.
Well,
I'm gonna take it to
hopefully, the Lie algebra L is said to be solvable. Right? Solvable. If for some m greater than or equal to 1, we have the mth derived, or you could say the mth product if you like, of the algebra is 0. He says, if L is solvable, the derived series of L provides us with an approximation of L by a finite series of ideals with abelian quotients. And this also works the other way around. That's the next lemma. Okay, so what's an example of a solvable algebra? Can you guys tell me some examples?
The completion of the reals?
Completion of the reals. Yeah, I think you're not wrong. The real numbers would be a solvable algebra because they are abelian, right? With respect to the commutator bracket, which is just AB minus BA, which is just 0, since real numbers commute. Yeah, so like an abelian Lie algebra is one for which the derived algebra is 0, right? So certainly any abelian algebra. Oh, wait a minute. Oh yeah, m greater than or equal to 1. Okay, yeah, we're good. So abelian is an example. He says the Heisenberg algebra. Which was that was?
That was when we. There was 2. There was.
What did I say that what was the bracket of it? It was, what was it? It was, in terms of the letters.
You had bracket FG equals Z, but you also did matrix.
Oh yeah, F.
Had E1, 2, bracket E1, 2, comma, E2, 3 equals E1, 3.
But you said it was E1 what?
E1, 2, bracket E1, 2, comma, E2, 3 equals E1, 3. And then hence E1, 2 was F, E2, 3 was T.
Okay.
T, sorry, and E1, 3 is Z.
So in this case, L prime, for the Heisenberg algebra, L prime is the span of Z, okay? Or the span of E1, 3 if you like, to talk about the specific matrix model of it. Now, what is L prime prime? Or L2 is what? See what it is? It's you know, you're taking brackets of linear combinations of one vector.
So it's just zero.
So the,
L2.
yeah, I mean, so this is 0. So therefore the Heisenberg, right? Therefore the Heisenberg algebra is solvable. M equals 2, as it happens.
Why do we call it solvable? This may be a dumb question, but what are we trying to find? Solve?
It is called solvable because of the analogy to solvable groups. Now, SL2C, right? Check this out, right? SL2C, we have equal to L gives what? L prime, which is LL, right? Equals to L. So in fact, LK is equal to LK minus 1 for all K. Well, I guess 2, 3. In fact, the derived series is constant for SL2C. So SL2C is not solvable. It turns out, and maybe this is premature to say, but I'm going to say it because you asked the question. This is an example of what's called a simple Lie algebra. So chapter 4 is working towards introducing these terms, solvable and simple. All right. I don't know off the top of my head. I think the honest answer is they're called solvable because they're, in the theory of Lie algebras, what are analogous to the solvable groups. And the simple Lie algebras are what are analogous to the simple groups. Simple groups can't be decomposed. They're sort of fundamental building blocks. A simple group is one which has no, how's it defined? Oh man. I mean, it has no interesting normal subgroups. In other words, a simple group is one which doesn't allow for any interesting factor groups. In contrast, a solvable group allows for all kinds of interesting factor groups. The term solvable ultimately is derived from its application to Galois theory, where you calculate for a given polynomial equation, you calculate the Galois group. If the Galois group is solvable, that means that over your base field there exists an extension field in terms of a radical extension for which the roots to your polynomial equation can be expressed in terms of the numbers in that extension field. On the other hand, if your Galois group is simple, it's not solvable. It's one of those polynomials where you cannot write the solutions to the polynomial equation equal to 0 in terms of in terms of the coefficients and simple algebraic operations of the coefficients. In other words, there's no analog to the quadratic formula for such polynomials. So I believe that's the honest answer, is that solvable and simple are given terms here because a lot of, and this is true of a lot of Lie algebras, is a lot of Lie algebra is built to be an analog to a corresponding theorem in Lie groups. I mean, at NC State there have been tons of people who have earned their PhD's thesis from basically taking a known theorem in Lie group theory and investigating its analog in Lie algebras. That has provided many, many thesis projects over the years. I'm not sure if that well is dry yet, but it might be. I don't know. Well, I mean, you can always start doing things over other characteristics, and I think, I don't know what the state of the art is at the moment, but in my lifetime, fields of characteristic 3 and 4 have been worked out for the Lie classification theory, if I remember right. I think the general verdict is characteristic 2 is hopeless. Everything's the same in characteristic 2. It's hard to see anything there. I say it's like that most recent Marvel movie, but I refuse to watch it. So it was. So you watched the the quantum.
Yes, it was awful.
It was awful.
Not even.
I knew it. I knew it.
You knew what? That it was awful.
I knew it would be awful.
Even if they like, for instance, like if you take out all the awful physics junk, that is not physically it makes no sense. But like even if you take that out, the story itself is just bad, in my opinion. So yeah, from a physics standpoint.
It didn't like win, or like I knew if Ant-Man didn't die, like I knew it was gonna be bad. Then you start chopping them off.
Yeah, it was unfortunately really bad. The only interesting character was the bad guy, I can't think of it, but no, it was, yeah, sorry.
All right.
I'm not saying more on video.
Lemma 4.3. My mic probably won't pick it up. Your secret's safe. That's not true. I'll repeat it. Let's see here. If L is a Lie algebra with ideals, L equals to I naught, which is containing I1, which contains I2, which contains all the way on down I m minus 1, which then is containing I m, and I m is equal to the 0 ideal, all right, such that the quotient of ik minus 1 by ik is abelian for 1 less than or equal to k less than or equal to m, then guess what? L is solvable. Whew, I'm starting to get tired. Maybe time for me to stop. No, we still got 10 minutes. All right. Let's see here. So, he says, we shall show that the kth derived subalgebra is contained in ik between 1 and m, and then putting k equal to m will then give Lm equal to 0. All right, so since L mod I1 abelian, this implies that L prime is a subset of I1 by lemma 4.1, right? So we have L mod I1 is abelian if and only if I contains L prime, right? So I1 has to contain L prime. That makes sense. Thankfully, I haven't erased that yet. That's very fortuitous, right? Now I'm really nervous to erase too much here. Well, we'll have to remember the definition there. I think we can get away with. I think we'll have to make do. All right, great. Now we're going to do induction. Suppose inductively that you have L k minus 1 is a subset of I k minus 1, right? Where k is greater than or equal to 2. But we know that I k minus 1 mod I k is abelian, right? Therefore, the product of ik minus 1 with ik minus 1, right, the derived algebra of ik minus 1 has to be a subset of ik. So here, ik is playing the role of I in lemma 4.1. And this is quote unquote L prime for ik minus 1. All right. But Lk minus 1 is contained in Ik minus 1. Let's see here. So this is assumed. This is a subset of what? See the way it goes? So if I drop k minus 1, it goes the other way. See, it goes the other way? Yeah. And this, oh. That's not what he says. I just wrote down something he didn't say. I'm sorry. I mean, I think that's true, but let me not write it. He says, all right, fine. But Lk minus 1 is a subset of Ik minus 1. By the induction hypothesis, so he's like Lk is equal to the product of Lk minus 1 with k minus 1, right? So this, dang it. I guess this is by the induction hypothesis right here. I have run out of energy for the day. I'm not, I mean, it's like, it's right there. Let me just.
Doesn't this just imply that it's a subset of IK?
That you said that's a subset. What's a subset of IK? That LK is a subset of IK. I mean that has to be the conclusion here. Therefore by induction, this holds for all k greater than or equal to 2, which then eventually forces L of, that, so since this, which then implies that, of course, Lm is a subset of Im, which is given to us to be 0, right? So therefore, Lm equal to 0, which shows that L is solvable, right? So I'm a little fuzzy on one of the steps right there, so I'm sorry about that. Let me move on here. Before I move on, though, let me just say what it's saying. It's like saying that, so the lemma 4.1 essentially says that, if we have this quotient being abelian, then I is contained in this derived subalgebra, right? This is kind of the other direction, right? It's saying that if you have all these abelian quotients, then it implies that you got a solvable, Let me say it another way. For a solvable algebra, we can set up this series of abelian quotients. But this lemma says the other way around, that if you have this properly, set up sequence of, if you have this stack of ideals, this sequence of ideals such that, they're abelian, one quotient one after the other, then it follows that your algebra is solvable. So it's, all right. Now, so here's lemma 4.4. It says, for Lie algebra, if L solvable, then every subalgebra and homomorphic image of L also solvable. Number one. Number two, if L has an ideal I,
What is homomorphic?
Lie algebra,
Homeomorphic?
no, Lie algebra homomorphic. So in other words, phi of L is equal to L2, and basically L2 is the image of phi. Then that also has to be a solvable algebra. And we're talking about Lie algebra homomorphism, so. If is an ideal I such that I and L mod I are solvable, then L is solvable. That's kind of like a divide and conquer thing, right? Like if you have an ideal and that ideal is solvable, and then you look at the quotient, right? The quotient ideal is basically squashing everything in the ideal to 0 and leaving everything else in L. So if you have those two pieces are solvable, it follows that the whole thing is solvable. It's kind of a, divide and conquer kind of theorem there. And then 3, if I and J solvable ideals, then I plus J is solvable. All right. Corollary 4.5. If L is a finite dimensional Lie algebra,